Welcome back to our case study of trying to implement a priority queue using a variety of simple data structures and the major operations. We have four operations a priority queue can implement. We can test if it's empty, we can add an element, we can find the minimum value, which we've been calling the peak min operation, and we can remove the minimum value. And let's see, I wish I left myself a little room to actually draw the data structure. There we go. And we've tried a number of representations using a dynamic array, and we have a favorite way so far, which is we have an unordered collection. The data is in no particular order in our array, but we keep track of the index of the minimum, and we found that that led to constant time operations for everything but remove min, which would run in linear time, because whenever we remove the minimum, we have to find the lowest value, the new lowest value, and update our index of min. So let's go back to, we were now looking at what would the running time be if we decided to use linked lists instead. So let's draw a picture of a linked list where the data is stored in increasing ascending order, which was the proposal here. And there's going to be good reasons why we might want it in increasing order if we're going to put it in order at all, because accessing the first element of a linked list is a constant time operation, and the first element will be the lowest value when it's in increasing order, and the lowest value is my minimum, and that's one I expect to access frequently. So let's go back to my favorite example of 2, 3, 5, and 8 being in my priority queue, and they're in increasing order in my linked list, like I said they would be, and we have a reference to the first node, the head of the list, and we want to know the running times. So how long will it take us to find the minimum? Well, we'll just look in the first node and get that value, so that's just linear time, right? The value's in the first node. Value in first node. How long to remove the minimum? Well, to remove the minimum, I simply need to, let's switch colors here. I simply need to remove this node, which means I need to change my initial reference to skip past the node with the minimum, and by doing so I've effectively removed this node, and now the list begins with that second element, and I can do that in constant time. I didn't need to walk down the list or anything. I needed only to change one pointer, some line of code such as head equals head get next or something to change the head of the list to refer to the heads next, which is the second node. So that would be also constant time. So just remove the first node. And finally, if I want to add an element, like if I want to add, say, 7, well, I'm going to need to add 7 in the proper place. Here, that would be over here. And that means, let's go through this real fast. I need to make a new node with the value I'm adding, but I need to walk down starting at the beginning of the list to find where to insert it. And let's go back to my pink color. Change that pointer to go to my new node, which is then going to continue to the old node, and this pointer is no longer here. And so potentially I might have to walk down pretty far. I mean, I might get lucky, I might insert the new minimum, and that will be constant time. But in general, I'm going to walk down this list a considerable ways, maybe halfway, maybe all the way, and therefore this is going to be a linear time operation because I need to find where to insert, which involves walking down the list. And if I look back at the running times we had so far, this actually is the same as the last representation in terms of the running time. If we keep our dynamic array in decreasing order, it was the add that cost us linear time and the other operations were constant. And we see the same thing here. And so that was pretty good, but we felt that we had something better going when we had remove in linear time, because I expect to perform remove less often than add, so I'm more comfortable with remove min being slower than add being slower. And that brings us to our last representation. Our last representation using linked lists anyway. And that's, what if we don't keep the linked list in any particular order, but we keep a reference to the node with the minimum? And that seems like a good idea, because before, our best option with the dynamic array was to keep track of the index of the minimum value in an otherwise unordered array. So here we're going to keep track of the node with the minimum value in our linked list in an otherwise unordered linked list. So let's draw that thing. We have some nodes. node is not particularly rectangular, but that's okay. There's another node like we had before, but this time our data values are not going to be in any particular order. So they're not going to be organized 2, 3, 5, 8 in ascending order. Instead, we'll keep them in no particular order. How about, let's go back, 8, 2, 3, 5. Let's try that order again. That worked out good for me. 8, 2, 3, 5. And in addition to having our unordered linked list, we also apparently have a reference to the node with the minimum value. So we have an additional reference. So not only a reference to the beginning of the list, we have a reference to whichever node happens to have the minimum. So in fact, I'm going to label these. This is the head, the first node, and this is the minimum, the node with the minimum value. So we'll have those two nodes as our representation. Now, we'll take a look at our three operations. Add peak min and remove min. And we'll determine the running time of each of these. Let's see, let's start with peak minimum. How long does it take to peak at the minimum value? Well, we have a pointer that goes directly to the node with the minimum value, wherever that value happens to be. Since I have that pointer, I can jump to that value in constant time. It would be something like min.getValue or min.data or whatever our syntax looks like. So, therefore, constant time. It's the value in the minimum node. In fact, maybe we'll call this thing min, go back there. Min node, so I can refer to it, we can keep track of it. It's not the minimum value, it's the node with the minimum. Okay, how about removing the minimum? That looks kind of tricky, right? Removing the minimum, that means I need to remove this node, which means I need to change the node before it to skip over it. So though I can find the minimum very quickly, to remove the minimum involves going backwards and skipping over it. There are a couple ways we could solve that problem. One is maybe instead of keeping track of the minimum node, maybe keep track of the node before the node with the minimum. And if I do that, actually we can improve upon remove min. Another issue is maybe we'll copy the 3, the next value, into that node, and then have this node skip over the next one. In other words, instead of removing the node that min node points to, maybe we'll remove the node after that and adjust the values so that we've removed the correct data value. But ultimately it's going to turn out none of these little clever improvements that let me update the linked list in constant time actually solve the problem, because I still need to update not only the linked list so that the data values are in order when I remove the minimum, but I need to update min node. And that means I need to find the new minimum, and there's no way to find the new minimum in my unordered linked list short of start at the beginning, walk down the list, find what value is now the new minimum. And therefore, there is no getting around this linear time. So even if I'm very clever about how I need to remove, find the new minimum to update min node is going to take us linear time. Okay, how about adding? Don't ask me why we went in this order. I'm not really sure. Adding an element. Well, where am I going to add nice and quickly? I'm going to add at the beginning of the list. So we'll just, let's say we're adding 7. So we'll just, maybe I should have done this in a different color, that's okay. We'll just change head so that instead of pointing to what used to be the first node, head points to my new first node, which I think I said contained the value 7. And in that way I can update the linked list in constant time, which is nice. I can add in constant time, except, I need to update min node also. Well, that's not too bad, because if all I have to do is compare the value I'm adding with the value that's the minimum, which I can get in constant time. And I can certainly compare in constant time. If that new value is greater than the minimum, min node doesn't change. If, on the other hand, we had added, let's say, the value 1 to my structure, I would compare 1 and 2 and discover, ooh, 1 is less than 2. No problem. I will just change this pointer so that it goes to my new minimum, and I can do all of that updating in constant time, much like before when we had our dynamic array with an index to the minimum. I could update the index to the minimum in constant time. So add to beginning, update min node, maybe. And I can do that in constant time. So overall, where do we get the bad time, the linear time? It's in remove min. And that gives us pretty much the same deal as when we had our unordered dynamic array, where we kept track of the index of the minimum. So representation 2 and representation 6 are, I think, my favorites so far. But I think in future videos we'll start exploring the idea of using a binary heap to solve this problem. And a binary heap is actually going to give us great running times. It's going to turn out not only can we peak at the minimum in constant time, but we can almost sort of split the difference between the bad remove min and the bad add. We seem to find that we either make remove min slow or add slow, and it turns out we can actually hit both of those in logarithmic time or better by using a binary heap. So that's something to look forward to in a future video. I hope exploring all these different representations of priority queues has been helpful. Hope you've gotten some good practice on using data structures and analyzing them using Big O. I'll see you in another video.